Okay, good afternoon and welcome to the EM course. This is a picture of NYSBC as I was walking into work this morning. We had a bit of snow, so this really is a winter-spring course. And this would be the view if you were to come on site, if we had this course on site. Maybe next year, and perhaps some of you would be able to tour NYSBC at that. Something that we always like to do when we did this in the short course is to have either a class placard or theme or design. So if you have suggestions, then I'll do some artwork and we can have some options such that if we have nothing but one background to stare at, as Micah and I talk and as other people talk, you'll be able to find meaning in it because you just created it. So you can, in chat or email, give us some suggestions. Something we're going to do, just a couple of administrative things. We are trying to record as much as we can. We do realize in this pandemic, Zoom fatigue is a real thing, and sometimes people are different time zones. So if you want to also watch and rewatch certain things, let's say you didn't catch it, the idea is not to have you focus on taking notes, but to be engaged. And that's the point of why we're doing the reverse classroom. So as you may see, if you go to our website, all the roundtables, which I'm calling what this is, and practicals are online. For those taking the class for credit, we do have worksheets online. In my email, I stated that it's due the week after, so I didn't give an exact time, but today at some point in time, for those taking it for credit, you should hand in the TEM worksheet. And if you're not taking it for credit and you're just curious, do send that in. Micah is our lead TA and he has the honor of doing the grading. So we'll see how harsh or lean he is this year. In terms of recitations, we have about half a dozen or so of you signed up for participating in our journal clubs. Micah will be the person curating that. And if you don't email us, we'll pretty much lock the email list by the end of this week, if not today, and we'll send up, and Micah will send emails for sign up. We have a particular schedule where we try to match papers with topics that we're going to go over. So if you want a particular day, you'll be locked in a particular topic. If you want a particular topic, then be flexible about your time. So let's get in today. Today we're talking about support films. So the first 45 minutes, Mike and I will start talking about support films. And Eugene and Mahara are going to segue to our dehumidified room in the last 45 minutes for a practical. This time we won't have breakout rooms. We'll try to be an all-in-one class. In our dehumidified room, we have a Leica GP and we have a VitraBot. So I am purposely going to skip some of the questions that people were asking about the Leica and VitraBot for when we have the practical, because we can actually see the machine. And if there are particular questions like, well, my machine does this, and we look, well, these machines don't, what's going on? So that could be the root of the issue, or there could be something that we're doing unconsciously as part of our SOP, and that has made the difference. So today we're talking about support films, and there were a few questions about grids and what are grids. We went over that in the lectures, but to be explicit, I want to go over some terminology. Grids are this 3 millimeter circle, and we call them grids because there's a pattern on it. So there can be many different form factors out there. They can be half grids, meaning not even a full grid. They can be in squares, hexagons. They could be finer grids, alphanumeric. Slot grids only have one hole. They could be made of various materials. If you go to the main trade show for EM electron microscopy, that's M&M. And so that's not just electron microscopy, that's also light microscopy, both on the material side and the biological side. You'll find grids made out of every material that they can manipulate, like from stainless steel, titanium, etc., all the way to the cheap grids, copper. It's not to say that copper is cheap in quality, but it's just cheap in terms of a material that you can make this 3 millimeter metal mesh. Most of the grids we use are made out of copper as a price point efficiency standpoint. As we're moving more into in situ work and cellular work, people use gold, and that's because that is very compatible with cells. So what did I mean by terminology? What is the grid? We'll call the grid the metal mesh. We'll call the foil the support film. And the foil itself could be continuous, lacy, and wholly, etc. So there's many different types of foils that can go on the grid. Now, depending where you go, these terms might be used interchangeably and people might have different nomenclature, but for the sake of this class, we'll try to use this type of nomenclature so we understand and we're descriptive of what we're trying to talk about. Are you talking about the actual grid, meaning what type of metal you're using, how many squares per inch millimeter, or are you talking about the backing on there? Are you talking about the continuous foil, the holy carbon, the holy gold, etc.? So I'm not gonna, if you have more questions about that, let us know. Otherwise, we'll skip. I'm basically doing it in order of when I received certain questions. So there's not necessarily a flow to answering one question or another, but it's in response to what people are curious in. There was a comment on stain and what protocols people use for staining. We tend to use certain elements, for example, molybdenum, tungsten, uranium, and some stains are in the lanthanide series. So there's the main thing for the stains is they tend to be electron dense, denser than carbon, hydrogen, and oxygen. And how useful is negative stain? There's always a question, like, do I even bother with negative stain? I would say negative stain is very useful, especially for a novel protein. If you're doing the millionth and one cryo-EM structure of protein X, okay, well, you might do negative stain as a spot check, just like you would run an SDS page gel as a spot check for your protein purification. But I wouldn't have negative stain be a barrier for you to move forward. So that's on a very established field. If you're a very novel field, there's some utility to that. The reason why this is modified is that our technique, Cryo-EM, is being more and more routine. So you can jump and skip certain steps. It really depends on your resources available and how comfortable you are. At one point in time, our workflow was to go through negative stain in addition to not only getting better biochemistry and better characterizing your sample, but to give people practice on manipulating all the tools required for EM before they go into cryo, because there was a separation between room temperature work and cryo work, especially when you're working on a novel protein and you're first going and putting your protein in ice. It's not so straightforward to know what you're looking at. You have to readjust. So the main stains we use are urinal acetate and formate, typically UA. So there was a question, so UA or UF? They're both acidic. Their pKa's are somewhere around 3. You can pH it somewhere around 4. We use UF in-house. UF is a little bit more labile than UA in the sense that you can make 1%, maybe 2% of these stains. And any further, it's not as water soluble. But given they're very electron dense, you get a lot of high contrast, and that's really good. So the UA is so shelf stable that I've seen some people make UA and just leave it on the bench for months. UF, if you make it, you would want to freeze it immediately. It's not as shelf stable. Okay. As I said, I'm going to punt a lot of the practical questions we had on plunge freezers. There are many different types of plunge freezers, from manual plunge freezers to assisted plunging devices. We're mainly going to be today talking about the Vitrobot and the Leica. And the Vitrobot, as we mentioned last time, is one of the most highly sought after devices and most widely used because of the throughput. Okay, so, oh, okay, so there is a question about, maybe I'll go back to negative stain. A question here is, what about negative staining versus cryo for lipid nanoparticles? Is there any advantage for doing cryo if you're only interested in looking overall particles and shape? So room temperature work has been used for morphology overall quite routinely because of the high contrast. So a lot of people love using negative stain because that method uses very little sample because of the high contrast and shelf stable. Once you stain something, you fix it, and you could save the grids and re-image them over and over again because the negative stain itself um, is quite stable for the electron dose that we're giving it. Cryo, some people move to cryo mainly due to the fact that because of the way you're staining your particle, there can be some dehydration, there can be some flattening, there can be some preferred orientation. The particular question was asking about lipid nanoparticles. Well, I know for nanodiscs, for example, it's basically like a pancake stack. It's very rare you would see nanodiscs edge on. It mainly is face down. You basically see circles. The only time is, let's say, the apoprotein, you're not using like a ligated apoprotein or some of the natural apoproteins, you'll see a nanoparticle or nanodisc stacks. And that's the only time we end up seeing edge on. So if the question is on that, in terms of other lipid nanoparticles, whether you're talking about, let's say, like maybe bicelles, or you're talking about vesicles, then depending on how large they are, it's sort of a balance where uh, negative stain might flatten a vesicle. So you would want, if you want to see, instead of ellipsoid vesicle, but a round vesicle, that's probably truly the shape in solution, then you move to cryo. The problem comes, as we're mentioning, if it's too thick. So if your sweet spot for vesicles are on the order of a half micron and above, well, it's very electron dense and you don't get too much transmission. Hopefully that answers that question. If you have more questions, just keep it coming in the chat. I see a few questions. There was another question on basically, I mentioned Alex Noble's paper about where protein sits. And I'm just showing you another figure to give the variation and give people a better understanding that when you're in bulk solution, our buffer in a vitrified state is a support film. It's supporting our macromolecule of interest. And as you can see here, depending on the, well, I guess I have some of the numbers upside down. I guess that's my slide. But you can tell that the protein of interest is not necessarily so uniform in the vitrified buffer. They can have preferred orientations. They can have air-water interface interactions. A lot of things can happen. Depending on how the grids are prepared, they might be more on one side than the other. How do I know what my protein is like? Well, after you do sample prep, you would empirically potentially take a tomogram, and from there you would know what my protein of interest would look like. I wouldn't know a priori unless it's something that we've done before. So there are a lot of interesting lateral interactions and interfaces that macromolecules could have. And what happens in solution, which can be very odd because the way that we make grids, we go from a low surface area, high volume to low volume, high surface area because we want things very, very thin. And making things very, very thin, you can have more interfaces and more potentiality of having interactions that are non-conducive to the health of your macromolecule. You could have denaturization, you could have preferred orientation, you could have other effects. Okay, so here is a concept of what we think may happen during vitrification. So if you have your macromolecules in solution, some sort of Brownian motion, diffusion, things are happening. And people have tried calculating how many times a protein of interest might interact with an interface, whether it's a support film, whether it's an air-water interface, etc. And they are trying to simulate what happens when you're doing sample preparation. You apply your sample of interest onto, let's say in this particular example, a wholly carbon grid, and things are just bouncing back and forth. Sometimes protein is sticking, sometimes protein is denaturing. Sometimes this layer can be protective in the sense that it keeps everything else in solution. And then if you're using a standard plunge freezer, you're blotting things away. And so you might have a situation where you're removing not only material of interest, but potentially proteins that are not what you're after. And there's an idea of if you have continuous carbon, that could be another layer to protect. So you can protect your sample of interest many different ways, through sacrificial protein, through support films, through other methods. Okay, so that is just a concept. The time scales of what happens greatly depends on what you're trying to do. Usually for a plunge freezer, there are many, many interactions with the air-water interface. I don't have the number in the back of my head, but there's a paper, there's a calculation that I know Chris Russo and Bob Glazer were trying to work out. How fast do you have to go to minimize the interaction? Can you go so fast that you, after blotting, prevent this particular interaction? So Micah, how I just showed you a cartoon. Does that even make sense, what I showed you?
Which cartoon? This one?
This one. Like, do you think this is what's happening to our protein?
Yeah, I think there's probably something to it. I don't know how universally it applies to every sample, but I think it's a good conceptual framework.
There has been a lot of talk about grid preparation because, as we mentioned, talking about what hardware developments do we want, or where do you think the field's going to move to? Right now, there have been different bottlenecks. It could be processing heterogeneous samples, low signal to noise. But the other side, if we could guarantee that my dynamic sample of interest is as close to an ideal sample as possible, then standard pipelines currently available would go as is. So the question really is, we still don't know exactly what happens when we try to do sample preparation. And something empirically we found, support films seem to help minimize some effects that we find preventative in terms of high resolution data reconstructions. So something that was talked about earlier is how do we help minimize preferred orientation would be detergents. Micah, have you used many types of detergents for your proteins? Is there a go-to detergent you would like to use?
Yeah, I have used both Chapso and DDM for two different reasons. I don't know if those are the best ones to use for those examples, but they are what worked. Using DDM for viral spike proteins seems to help. If you don't use it, the complex seems to fall apart. So we usually look at spike proteins with antibodies. And oftentimes we find that there are no antibodies bound, or there are fewer antibodies bound than we would hope, or the whole spike is just fallen apart. And then we add detergent and things look a lot better, and we have no idea why. I used Chapso on a protein that had some preferred orientation issues, and that seemed to help. It still had preferred orientation, but it was a different angle of preferred orientation. So then I could combine the two data sets and get something that was less anisotropic than what I had before. But I don't know that there's like a preferred one, you know, I think.
Would you use NP40 or Triton?
Probably not. I don't know. I tend to stick with ones that I hear people talking about for EM, and I don't hear a lot of people talking about Triton or NP40.
It's like people are doing a Western blot, or people are just solubilizing cells. They have a ton of that, and I've heard it used, but that's anecdotal. And if you go to, I mentioned this before, certain places sell kits for improving vitrification. And they basically did the heavy lifting of going through all the journals and saying like, okay, which of the products I sell could potentially help you? So therefore I'll repackage it. And not NP40, I guess in this case, Tween 20, the same idea. Tween 20 and Triton X are on there. I don't know.
People use them.
People use them. So I haven't used them myself, and I'm just curious. I just hear it in anecdotes. So, but that's exactly right. So Gerald was saying, like, the guess is that detergents could crowd out the sample molecules. Here, maybe keeping them away from the surface. What's our guess? So there have been, was it Eduardo? I'm blanking on his last name. Did that study where there's denaturization in the air-water interface, and detergents can help mollify that. Graphene oxide can help mollify that. We'll hear more about that later. But detergents overall, I would use sub-CM, unless I'm working on memory proteins, sub-CMC concentrations, because we're not trying to solubilize anything.
But what I've heard is that they just act as surfactants, right? They coat the air-water interface and keep proteins away from the air-water interface. One thing that, I mean, I don't know how universal it is, but it's been true of basically every protein that I've worked with, that I've added detergent to the sample. You always need to increase the concentration of the protein pretty significantly, sometimes as much as a factor of 10. So for some reason, and this I really don't totally understand. You have to, you just see fewer particles if you use the same concentration of protein and add in, 0.005% DDM, which is, half of the CMC, then you see almost no particles. You up the concentration and then everything looks fine. So weird things are happening, and sometimes it can help.
My hypothesis is that because you're removing interaction, so there means there's less of an air-water interface concentrating your sample.
Yeah.
So you would need to up the concentration, otherwise it's just less dense visually in projection. We had a follow-up question. So are you coating the whole grid and drawing the particles elsewhere? And it could be, if you're using surfactants as sacrificial layers, then you need enough to cover that whole layer. That could be quite a bit, depending on how expensive a detergent is. We would just add it to the buffer and plunge freeze directly. What do you do, Micah? Do you do it in your storage buffer? Do you do buffer exchange, like size exclusion in the detergent, or do you spike and go?
I usually just spike and go, leave it there for about 30 minutes. It's usually not terribly precise. It is, I get my sample out, I add some detergent, and then I go set up the plunge freezer, go discharge my grids, and then by the time I'm done with all that and ready to freeze, it's been maybe 30 minutes, and I freeze things then. But again, a lot of this stuff is, if I started seeing problems with my sample, I might adjust that, right? I might do less time in detergent, more time in detergent. There's no real hard and fast answer to a lot of these sample prep problems. You just have to try things. Try different detergents. If one doesn't work, try a
I'm
different
not
one.
sure that I would add glycerol. I mean, maybe that would be helpful. I just fear adding glycerol because it makes things very viscous. It's not like it's going to be honey, but it changes the surface tension and the properties.
Yeah, I don't think I've ever. I may have frozen a couple of grits with glycerol because they had glycerol in it because I had frozen the protein and added that as a cryoprotectant and didn't feel like removing it. So I just threw it on the grid to see what it would look like. But
there's not DMSO. I heard another anecdote. People were looking at small molecules and it was dissolved in DMSO. And so they did a control with just DMSO and DMSO with ligand, and the DMSO helped. I don't know why either. So it's sort of like just random things that you throw in. I know of an X-ray crystallographer that told me they used IPDG as an additive in their crystal screen, and it helped. And it was just very peculiar for the protein they were working at, but not because they wanted to induce protein in a crystal. It's just they had it in the lab, they threw it in.
right, yep, and it worked.
Okay, so we're getting towards the end of the questions, but there are a lot of things that come up. Like, I have a particular sample. What can I do to help it? There was a comment on cross-linking. There were a few comments on graphene oxide. Fortunately, we have someone that is trying to make graphene oxide and graphene grids more routine here. And that is Eugene. So if Eugene can unhide himself, perhaps he can talk a little bit more on his journeys into making graphene grids.
Hi. So I've tried making both graphene and graphene oxide grids, and the idea is that you want to float a single layer of graphene or graphene oxide onto the surface of your holy carbon grids or holy gold grids. And that gives a single atomic layer of graphene on which your proteins can adhere to. And this is good for doing things like concentrating your protein on the surface without the drawbacks of having lots of background signal that comes from having lots of carbon in your holes. Yeah, generally my experience has been that graphene oxide grids tend to be easier to make. We can purchase graphene oxide from Sigma in a liquid suspension, and all you have to do is dilute it and then float it onto the surface of the grid, the same way you would do, say, like carbon off mica for making negative stain grids. With graphene, monolayer graphene grid making, it's a lot, at least the protocol that I've followed, which is from a Princeton lab. It's very involved, and it requires a lot of manual skills, which maybe I'm just not very skillful at it at the moment, but my yield is not so great when it comes to these graphene grids.
You know what their reported success rate would be, or what would a good success rate be for you?
Well, they didn't, at least I don't recall them reporting what their success rate was. But for me, I've tried it 3 times now, making these graphene grids following their protocol. And I would say I average about a 50% yield of graphene grids. And that's just the grid itself. So catching a graphene flake on a grid, I get maybe about 50%. I lose 50% of it through maybe like the graphene layer sinking into the liquid, or me not being able to see the graphene monolayer because it's a single atomic layer of graphene and I'm trying to look at it with my bespectacled eyes. So there are several challenges, but I'm hoping to be able to optimize the workflow a little bit more so that we can have a better throughput and a better yield success rate of the graphene. But once the graphene is on the grid, actually it works, and I can get protein on it, and I can see diffraction spots on the graphene. So that's really that's nice. Yeah, but just my novice experiences working with both graphene and graphene oxide, graphene oxide is just a little easier to manage. Yeah.
I'm going to stop screen share pretty soon, but the idea would be if I were to leave up the slide, we're taking suggestions, and please do that. And otherwise, I'll just put a blank slate, literally a blank slate up, as you see here. We have a lot more questions, and we'll start talking about that. There was a question of what type of sample should I use for freezing? Like, do you use fresh? Do you use frozen, like freeze thawed? Whatever works. I would say if you could freeze your protein, that makes it a lot easier because you can time shift sample generation from plunge freezing, but that might not always be available to you. So Micah, have you ever had to do the marathon of off column to plunge freezer?
Yeah. We have definitely worked with a couple of proteins that were very unstable. And it was basically, it came off size exclusion, and as fast as I could get it over to the plunge freezer to freeze, I did it, which is nice. We have a nice one of the Biorad FPLCs at SEMC, so I was able to make use of that. But my lab at Columbia also now has a VitraBot, so I could do my sort of normal protein purification and then go over to a VitraBot. But I think that's generally better, unless there is some other biochemical reason why you would want to wait. I've heard of a couple of proteins, if you need to incubate it with something, or if you need to incubate it at a higher temperature, I've had some proteins that, I need to switch pH after I purify. So those things are going to sort of necessarily delay it. But, lots of like, well, what do you do with the protein is, these are questions for, well, you better than we would. Fresh protein is probably usually better, but that's a biochemical thing. I will say that I have taken protein. I have published data of a protein that had spent 3 days spinning in an analytical ultracentrifuge at room temperature, and then we pulled it out of the AUC, and then I made grids with it and got good enough data to publish. So sometimes things just work.
Wonderful. So I guess it's really what works. If there's no barriers and you can just go grow cells from culture to grid in as fast as you can. I think they did that rush for the SARS-CoV-2, right? The first one, they just basically went straight through.
Yeah, our all of our SARS-CoV-2 stuff is fairly high throughput. I don't think we ever did negative stain on them. I don't think we were on the first thing we did was make grids and throw them on a Cryos. But when you have several technicians just working on purifying protein, and then you have kind of an established protocol for viral spike proteins and antibodies, you can do that kind of stuff, but usually not.
We have a question on, is there a way to measure ice thickness? Then there's multiple ways of measuring ice thickness. So I think the question is really asking like, okay, of my protein in buffer, what's my ice thickness? There, you could use mean intensity to a reference. You can use aperture limit scattering. You can use energy filter. You could actually drill a hole and tilt, and using trig, figure that out. You could also do that technique to look at your contamination rate. So that's something that we don't really talk about. Over time, your grid just sitting in a microscope, the sample gets thicker, you have loss of quality. So some instruments, let's say with IGP and everything, you can keep it there for a week, maybe 2 weeks, and you see negligible. You would see like only an angstrom or two difference. So basically it's negligible. Some screening microscopes, you put it in there, and by the end of the day, your grid is twice as thick as you put it in. So that impacts it. But I believe the real question was asking like, okay, I have my sample in there, how thick is it? You can do tomography. You can drill a hole and tilt and see what it is, or you can use a proxy where by the inelastic scattering going through, if you calibrate the free mean path, you would have a way of guessing really accurately what your ice thickness is. And there's a paper on that. And we might, if I dig it up, I'll put it on the website, or maybe I'll just email that out. Next question, could you comment on the new hexafoil grids and challenges with collecting data from these? So there is many different form factors of grids. So you might ask, like, why did we use square, like grids, like meaning grid squares, or why do we use squares? Why don't we use hexagons? Why don't we use other form factors? Well, they exist, but for single particle, traditionally what we used were just, the bare grid was grid bars in squares, and we overlaid foil on them that's either continuous or wholly carbon. The new form factors allow higher throughput data collection because there's more holes. So the difference between negative stain continuous carbon grids, it's a continuous carbon, but for cryo work, the carbon has holes in them, and it's usually a regular array. And the question is, why is it a regular array? Well, it's easier to make the mold and pattern for it, but you could have different hole sizes. So the newer grids not only have a different, we use a different, instead of squares, but the hexagons, but you could also, for the holes in the carbon, use different hole sizes and different array types. It makes it faster because we do beam image shift data collection. So we're not stage shifting to do every single image. We're tilting the beam to get more images per stage shift, and that is higher throughput. That requires better calibration, because if you don't tilt the beam correctly, you add aberrations. Also, if the beam diameter is too large because of the optics of the microscope, then your beam might be greater than your hole, and you'd be burning other holes on that support film. I don't know if anyone has anything to add, or if that answered the question.
Was the question about the hexafoil specifically?
The hexafoil grids? Oh, it's hexafoil specifically.
Yeah, I'm gonna share my screen. I don't know if I can. Yeah. So the question was specifically referring to grids that came out of this paper, Cryo-EM with sub 1 angstrom specimen movement from Chris Russo's lab. We actually reviewed this paper, and in that process got a couple of grids from them to sort of mess with, but this is what they look like. As the name suggests, they are, the grid bars themselves are hexagonal. So instead of squares, they're hexagons, because you can pack more of them together more tightly. You can see these sort of like zoomed out. I really wish that legend didn't show up. A and B show the sort of like zoomed out view. C is one of those squares. And in D, you can see the support film has holes in it, as we've sort of come to expect. But the standard diameter for those is usually between, on the very low end, 600 nanometers, and more commonly between 1200 and 2000 nanometers. And these are a fraction of that. You know, these are 200 nanometers in diameter. And then an F, you know, it's zoomed in with some very nicely packed apoferritin in there. So benefits, you can collect data very quickly because all the holes are very close together. Like Eb was saying, you can do this beam image shift, and you can get more of those holes in a low mag image than you could if they were larger holes spaced out further. But that they don't talk about that much in the paper. They kind of mention it, you know, that you can get increased throughput with these. But the point, as the title suggests, is that you get a lot less movement of your sample. Maybe one of these figures will show what it's talking about. I was kind of hoping one would illustrate the point. Oh yeah, this one does. So what normally happens is what you can see here on panel D of this figure. You've got your support film, you've got a layer of ice, and when you expose it to the electron beam, we believe there is this doming effect, that the buildup of negative charge on the sample causes it to sort of rock back and forth, and you get a lot of movement of your sample as you're collecting the image, which obviously is bad. You can see the displacement over here in this gold particle in the bottom left-hand corner. We do motion correction, which is something we'll talk about when we do our processing practicals, and we'll probably talk about before then, but you'll actually do in our single particle processing practical. So we can correct for this because we're taking movies and not just still images. But there's a bit of movement right at the beginning that is kind of hard to correct for if there is a lot of movement. And apparently working with these really, really small holes, there's a ratio, which is actually what they show on panel E, a ratio of the thickness of your sample to the diameter of your holes. And if you're in this sort of regime, approximately an 11:1 ratio, apparently you don't get any of this buckling. So you don't have any movement, or at least, again, sub-angstrom movement of your sample, which is a lot less than what most grids will give you. So that's why they do it. They test these points. Those points in panel E are the ones that they test to kind of prove this, I guess. So that's the benefit of them: throughput, reduce sample motion. This is a really cool thing where, because there's no sample motion, they can, all of the B factor that they calculate in their processing, they hypothesize is only due to sample damage. It's only due to the buildup of dose and the damage of your sample. So they're actually able to like back calculate a map that is a sort of theoretical zero dose map, which I thought was really interesting. The downside is, as you can see in this image on the right-hand side, panel F, you get a bunch of the gold clipped into the image. And this is a fairly high mag image. If you take it at sort of a standard magnification 1 angstrom per pixel, you get something that actually kind of looks like panel E. You get a lot of gold and a little bit of sample, and it actually becomes really difficult to calculate the contrast transfer function, which is a very important step in pre-processing. So because you have all this gold, and that kind of throws some of the normalization off, and it throws CTF estimation off, that's a challenge in processing data collected on grids like this. But it's doable. It's just a little more labor intensive, I would say. So whether or not it's worth it for your sample, I don't know. We'll see.
The beam is usually larger than the hole to minimize that motion. But I remember there would be delocalization, wouldn't there? There was a paper on that, right? You would see the delocalized pairs when you hit the gold. That might spill in the image as well. Not just gold diffraction.
Right.
So then that's you have other Fourier components of like objects that are not even of interest.
Yeah. So some aspects of the processing can get a little weird, but I think it's certainly an interesting idea. I wouldn't be surprised if we can like figure out a way to more routinely get over these processing issues, which I think there are ways to do it. You know, those grids I don't believe are commercially available yet. As we were reviewing the paper, we asked for some of them to try out because we had some ideas of other experiments to do. And they sent us 4 grids total. So even in like putting in a personal request, we only got 4. So it might be a little while before they become commonly available. But once they do, I wouldn't be surprised if you see them become more standard. But a lesson that you can take away is, especially if you're doing like tilted data collection, where that sample movement is really exaggerated and can be a more significant issue, try using smaller holes for your sample, especially if you want, and this is what was counterintuitive to me, if you want really thin ice, if you have really thin ice in a really, really large hole, you're going to have an exaggerated amount of that doming, and that can make motion correction difficult. So if you either can get or really want to get a thin layer of ice, which I think most of us do, it'd probably be beneficial trying to accomplish that with as small a hole as you can sort of get your hands on.
So on this topic, the foil, as it were, is made out of gold. You can make them yourself. You can buy them from Quantifoil, and now C-Flat has gold grids. Micah, do you have experience with either? Do you prefer homemade ones versus store-bought ones?
I think I've only really regularly used homemade gold grids. I don't think, well, because buying them commercially just takes way too long. So I usually just get carbon grids. We have a gold evaporator in the lab. So I evaporate a layer of gold onto standard carbon grids, flip it upside down, and then throw it in a plasma cleaner for a couple of minutes to sort of remove the layer of carbon. And then you've got a nice, you got nice gold grids. But I like those because you get to control the thickness of the layer of gold, and I find that they're usually much thinner than the commercial ones that I've used.
Right. Do you notice that you need more or less protein when you're on gold grids versus carbon?
I haven't really done any kind of like systematic study. At this point, I pretty much default to gold, and I will only try carbon if gold doesn't work, which has happened a couple of times. I don't know why, but I've had a couple of protein samples that really looked terrible on gold, and I could have spent a bunch of time trying to optimize it, but found that I switched to carbon and everything looks okay. So I don't know that I've really tried both. Trying to think if I've heard anything.
Of grids, we use both quantifoil and C-flats. Quantifoil has thicker support film in general, if you're talking about the carbon ones, than C-flats. C-flats are thinner. You can tell that because if, let's say, you plasma clean grids head to head, I can plasma clean a quantifoil for 30 seconds, turn it upside down, another 30 seconds, and it's fine. If I were to do that with a C-flat, it would probably be broken. In terms of gold C-flats versus gold quantifoils, we mainly shift to gold recently because of what Micah was referring to. It reduces motion. So if you just help every step of the way, like you have a better sample, better processing, better everything, then the workflow, you can sort of squeeze out, those tenths of angstrom better resolution. But what you just saw in the graphs that Micah showed, when you're on gold versus carbon, there's less motion. There's a lot. It's more stable when you're tilting. So there's certain labs that, because they just keep on buying gold grids or it's not back ordered, they're just exclusively using gold grids. I've also heard, can you reuse gold grids? I've heard of labs, because of the price point of gold grids, because they're expensive, or at least more expensive. And then when you're dealing with, tens and hundreds of grids, then that really adds up. You could clean it. I think the main problem is you just have to minimize manipulations, because you can damage the grid. You can bend it very easily. So I've heard people trying to do an acid wash, chemical clean, and then reusing them. Most people just buy grids because, or again and again, because they consider them consumables, meaning I bought this grid, I plunge froze it, but I'm not going to recycle it. Micah, I guess, were you ever asked to reuse anything in your lab? I guess grids, pipettes, anything. I mean, it depends on the lab, right?
It definitely depends on the lab. So not anything at SEMC. We did switch over to reusable cell culture flasks in my lab at Columbia, because the disposable ones were just getting absurdly expensive. So now we clean our cell culture flasks and autoclave them and then put them back before we use them again. But in my lab in undergrad, yeah, we reused everything. Absolutely. We had like a couple of pipette tip boxes, and we would buy the big non-sterile bags, and we would have to sit there and fill the pipette tip boxes
at the end,
and then autoclave them.
Oh yeah, I remember.
So
that's what I did when I undergrad. Okay.
Yeah, that lab had a lot less money than the labs that I work in now, because we did plant biology, which nobody really wants to fund. No NIH money for that. So yeah, grids are disposable. I've heard of people reusing auto grids, clip rings and stuff, but I don't think Thermo Fisher recommends that. You might void the warranty on your Cryos if they find out you're doing that, so don't do it.
We don't reuse here. Okay, this is the last question before we segue to the practical, and this is an appropriate question. Do we have suggestions to prepare samples / grids for complexes which do not last long in solution? For example, transient protein-protein complexes. Well, you know, spotted on. Time resolved spotted on is a useful device. So there's time resolved plunge freezing devices or alternative blot-free vitrification devices that have 2 dispensers. And if you have a very transient interaction and you're trying to capture that, that would be less than the time it would take you to manually plunge freeze something in, let's say, a Vitrobot. That would be an avenue. But if you were to do it in a Vitrobot, you might try changing temperature or adding other things. So Micah, how many grids do you make normally versus any of these non-blot devices?
Usually end up making about the same number. Or are you talking like total throughout a project?
Throughout a project, meaning, or do you have any projects that you noticed that it was very labile or it was hard to capture an intermediate?
I've never worked on anything time resolved. I have used blot-free vitrification devices mostly to avoid issues with the air-water interface. So I wasn't mixing protein samples. I was just trying to vitrify them as quickly as I could. Those, well, I'm probably not. I ended up making way more on chameleon / spotted on than I did with the Leica, but mine was an admittedly unique and kind of challenging case because I was trying to, we were home making spotted on grids, gold spotted on grids, which if you get a chameleon, you get grids for your chameleon device, but they're carbon. They're always carbon because we grow these nanowires on carbon grids. But in-house, you know, we've experimented with coating those in gold, and they're just a little finicky and they're very difficult to work with. But I really needed gold because I was tilting my sample, and on carbon grids, the beam-induced motion was so extreme that I couldn't. Motion correction was a problem, and my reconstructions were suffering because of it. So that one, yeah, was pretty labor intensive, and it was a lot of like not just messing around with vitrification, but messing around with like how do we make the grids in the first place. But I don't think most people are going to encounter that. Usually the blot-free systems work fairly well and are pretty consistent. If they're not more consistent, you get some feedback on at least ice thickness before you put it in the microscope, which you don't get for basically any other technique. You freeze, you throw it in the microscope, and that's when you find out. But with spotted on, because we have this camera and we can observe the wicking procedure, you can get a good sense of how thick your ice is going to be before you put it in the microscope, which saves time.
And this is the perfect segue because we're going to go into the dehumidified room where Eugene and Mahira are going to show us plunge freezers. And some Leicas also have cameras. There's a mode that Leica supposedly smartly knows when it gets thin enough to do some plunging. So let's see which device are we looking at first. You can see Eugene and Mahira, they're in our dehumidified room. One useful thing maybe is to just give our audience an overview of what is in a dehumidified room or what we consider useful in a dehumidified room. So hopefully through their masks, we can hear them. Or
Oh, are we talking?
okay, you have an echo, but yes. So you might notice Eugene and Mahira have 2 cameras. You can see the room and you can see Eugene on the opposite side. So let's try to dual view both of them. So yes, please do annotate what you're seeing in a dehumidified room.
Well, we have a Vitrobot over here on a table. there is a, yeah, we've got liquid nitrogen dewars. Let's see, behind Mahira is a Leica plunge freezer that is currently doing a bake out. We have an ethane tank over here. storage dewars underneath the tables for storing samples in liquid nitrogen. Various cryos tools like nanocabs and just like liquid nitrogen containers that we use for handling grids for the cryos. This is a transfer station that we use to load up the cassettes for the cryos. Let's see, heat blocks. This here is like a little heating, a little oven that we use to dry our nanocabs and other cryos tools. Clipping station for clipping grids. Yeah, there are some other instruments here. I guess it's a carbon coater, the ACE, and I don't know what this BCM is, but for doing cell stuff.
It's a transfer station for the Leica shuttle for if you want to make lamella.
There you go. Yeah, so that's what's in our room, and we have operators like Micah in here.
They don't come with the room, do they?
No, yeah, that's what's in here. Yeah, and today we are doing a demonstration on the VitrBot. So, what's your camera pointing at, Micah?
Yeah.
Okay, I don't know which one to look at. Trouble.
I mean, you're gonna be doing, so I'll be the moving.
Okay, so we have this is the VitrBot. We have the on switch is at the back, actually at the bottom right. Let me turn it on. So this is like a control panel. Can you see it? Yeah. Okay, the control panel where you can set your settings for vitrification. You have the chamber for vitrification where the blotting happens. You might be able to see. This is the blotting chamber. There are two pads that will connect those in each other to blot. And your sample goes in there, obviously you pipette onto your grid. In this chamber, it's a humidity controlled chamber, so you can set the humidity. You have a humidifier container here that gets connected to the bottom of the sample chamber. Let's see. That's right.
Yeah.
Yeah, it gets connected at the bottom, and we fill this guy up with water that will humidify the chamber. And we have an ethane lift right at the bottom here that will lift the ethane in liquid nitrogen up for the plunge freezing to happen. And in order to get to that, to make use of this, we need the ethane thing. We have a styrofoam container here, into which there are several parts that need to be assembled for preparing the ethane. So you have a styrofoam container with a stand in the middle. This is bronze thing is an ethane cup. It goes in the middle. We have a holder for holding grid boxes that goes in. And we have a spider that is used to place on top of the ethane cup. It connects the ethane cup to the liquid nitrogen. And what we want to do is fill the surrounding well with liquid nitrogen, and so that it's the nitrogen shouldn't be in physical contact with the ethane, otherwise it'll all turn solid immediately. And yeah, so what you want to do is use the nitrogen to cool down the ethane cup such that it reaches close to liquid nitrogen temperatures. Then you can liquefy the ethane gas inside the cup. So this spider helps to provide the thermal contact. We also have a styrofoam and anti-contamination ring. Usually it's floating on top of the liquid nitrogen like this, and it just helps to contain the nitrogen vapor. Gives you a little bit of wiggle room when you're moving liquid from the ethane into the surrounding liquid nitrogen. Although I've seen people work without this before. So this is what you need. Preparing for vitrification, we need to usually we need to switch on the vitribot, depending on your settings. But if you are going for 4 degrees, so I don't know if you can see the screen. Can you see it?
Oh no, you can.
Okay, you can see what's on the screen. You can control the temperature. So if you want it at 4 degrees, you need to set it something like between about 45 minutes to an hour beforehand, so that it can actually cool down. You have a little matchstick that you can use to point. You can turn on the humidifier to 100%. So yeah, depending on your conditions, but I typically use 4 degrees Celsius and 100% humidity. Yeah, and we'll need to fill in the humidifier. So just some water.
It'll fit in there.
So 50 to 60 ml. Goes in via the injection port here. You could. Somebody can address the question.
I can ask you, it says, I found difficult to control eye thickness when using detergent. Do you have any tips for low audience? How about?
Oh, sorry. Maybe Micah could comment on this because I don't have much experience working with detergent ties.
Yeah, I have experienced some of the same issues. Seemingly every time I add it, I end up with thicker ice than what I would normally. I haven't found anything that works. You can try blotting for longer. Glow discharging more. I really don't know. I'm sorry I can't be of more use, but I have experienced some of the same issues. So
with detergent, you change the surface tension, and therefore the way it spreads on the grid changes. And yes, very typical is that the holes are thicker than the support film because of the way the surface tension goes. And that is also a pain when you're setting up automated data collection because the hole finder can have trouble.
Yeah, Ed spent a lot of time early on in the pandemic manually queuing up my SARS-CoV-2 stuff.
It was
sorry about that, Ed.
It was so important. We were all trying to pitch in, but that was like the everyone was saying like you manually targeted it. About what we really mean is like we say every single acquisition point we specify directly because usually everything is automated, and people forget that you might get carpal tunnel by clicking a couple thousand times.
All right, thanks, Micah. So maybe what I could do is to try and speak up a little bit and also do a dry run, right? We have typically you would wait, you would check the control panel and make sure that the vitribot is at it's stabilized at the environmental conditions that you need it to be at. But since we're not actually making a proper sample today, it doesn't really matter. So these are the vitribot tweezers. They are a special set of tweezers that are very expensive that fit the vitribot. Especially they have this little notch on over here that I'll show you how it fits in a second. But before we do any of that, you want to take your grids and you want to, well, typically you would glow discharge or plasma clean them in order to make them hydrophilic if you want. But you would prepare your grids. On a grid block or on a glass slide or on some filter paper, however you prefer. And we plasma clean them usually as a pre-treat. Oh, yeah, I always forget stuff. Blotting paper. So yeah, we need to put in the blotting paper, otherwise nothing is going to get blotted, I think. So these are, we can purchase pre-cut blotting paper. Otherwise you can cut your own also. As such. And in the VitraBot, we have these little devices that hold the, this is like the black thing is a sponge kind of thing. And so all you want to do is just put it in place, put the blotting paper in place. So I do it on both sides usually. And when I do it on both sides, and usually when I'm installing the paper, I use it as hand on the, place a hand on the back side of the arm to stabilize it. Yeah, so that I'm not breaking this thing. Okay, so yeah, before you start, you definitely want to put in some blotting paper so that you get some blotting action. And usually, so I know last week Micah talked about this, that he puts in the blotting paper, you know, like X amount of time before he starts vitrifying. And so I usually put it in just before I start cooling down and start making the ethane. So then it maybe takes me like less than 15 minutes, but maybe 10 to 12 minutes to make the ethane and to cool down the nitrogen, cool down this thing enough, and to get all set up for the vitrification, right? So so I've let the blotting paper kind of humidify itself in the chamber for maybe 10 or 12 minutes before I start vitrifying. So that's just what I work with. Yeah. So yeah, you want it set up. You want the ethane container set up in this way, and basically you pour nitrogen until it's cold, and then you would liquefy the ethane in there, remove the spider, and replace it with the anti-contamination ring. Okay, it's not floating today because there's no nitrogen, but we put it here in the ethane lift. Yeah. Okay, and one last thing that we need to prepare is the blotting condition. So if we go to the control screen, there's an options button here. Can we see it? Yep. So if we click on options, we can choose our options like blot time, wait time, drain time, blot force, etc. And these are the important parameters to take note of when you're blotting. Each VitraBot is, well, from my experience, every VitraBot is different from the other, and you kind of have to determine what good blotting parameters are for that VitraBot, and also for the grid types and sample type that you're using. Right? So you have options also on the miscellaneous options on the site, whether or not you want to use the foot pedal. Usually I select all of them. So I turn off the humidifier when the grid is in the chamber, skip grid transfer, and auto rate ethane lift. That's how I prefer to use it. But you can definitely customize it as you like. Okay, so the first thing to do is to place a new grid. So I'll click on place new grid, and if you can show the chamber here, you will see the yeah, you'll see that there is the arm comes down that holds the tweezers. Okay, so with the tweezers, I'm going to pick up the grid. Of course, I'm not going to do a good job when I'm demonstrating. Okay, so can we see it? Grid on tweezers.
Yep.
Great, and we're gonna install it onto the arm. Okay, I can't move my finger. You can see it. All right, so it just clicks in place onto the bottom of the arm that protrudes out there. And you press, on the screen, you press continue, or if you have the foot pedal enabled, you can step on the foot pedal. What it does is brings up the tweezers with your grid into the chamber. And because I have auto raise ethane lift, the ethane lift is going up, and it's bringing the ethane directly underneath the chamber here. And if you look inside the chamber, there's this little white notch over there. It's later on, it's going to move to the side, and there's a little hole there that the tweezers will go through to plunge your grid directly into the ethane. Okay, so the grid is now in the chamber, and we press on either the foot pedal or on the control panel. You click on start process, and the grid will be moved to a position where you can apply the sample onto the grid. So take a pipette and take like your preferred volume of sample, let's say 3 microliters. And there are ports on the side that you can open. You can see here this red port that you can slide open if you're left injecting or right injecting. I think, yeah, I'm a left-hander, but I always inject it from the right because that's where everybody does it. And it's important to keep it consistent. So you just want to approach the grid and pipette your liquid into it. So close the chamber and then press continue. Grid goes up. So I've set a wait time of 10 seconds. So it's waiting now. After 10 seconds, it will blot for 4 seconds. And then the grid will be plunged. Oh, there we go. Blotting for 4 seconds. And now it's been plunged into the liquid ethane.
There was a question, you kind of answered it, but I don't know if they want me to type an answer. It's, do you let the filter paper get wet before blotting?
Yeah, yes, I do. I put the filter paper in to the chamber just before I make the liquid ethane. Okay. And that gives it enough time for me anyway, that's how I do it. Okay, so you might be able to see now that the grid is in the ethane cup, in the ethane. And what the goal now is to, and of course I again forgot something else. You need a grid box to move your grid into. So you can do this after the fact, but it's a lot more tricky to do it. I mean, you should be better prepared than I am. Yes, cool the grid box down before you start. But after the fact is also okay. And so what you want to do is, what we want to do then is move the grid from the ethane into the liquid nitrogen quickly, but there's no need to panic in the process, right? Just be quick but steady. So this process is a little bit involved, and usually I practice a few. When I was learning this, I had to practice a few times. But the idea is you have to first disengage the tweezers from the tweezer rod, and then you want to lift up the black thing that holds the tweezers close together. But you don't want to let go of the grid, so you have to use your fingers to hold the tweezers closed so that the grid stays on the tweezer, right? So first thing to do is to remove the tweezers from the rod, like so, right? And then I always rotate it, and I hold. I don't know if you can see this. I hold the bottom part of the no, that's good. I hold the bottom part of tweezers with one set of fingers, and then I use the other set to lift this up and to hold it up, right? And so now I'm in a good position. I count to 3, take a deep breath, and then move it into the liquid nitrogen like that, right? And then I slowly guide the grid into the grid box. And then there we go. And then there's a little lid that you want to, okay, the screws are on a little bit tightly, but you move, I usually poke it and move it to the next slot. Take out the tweezers, warm them up, dry them up rather, pick the next grid, and then continue on. Yeah, so that's how I do it.
Could you show the Leica GP just that it's on one-sided blot instead of two-sided, and attachment of the filter paper just for a point of comparison?
Do you want to do it? I'm not very familiar.
Tell me what I'm seeing. Okay. Can you see?
Okay, yeah, so ready for machine learning.
Okay.
Yep. Okay, so yeah, there's only one side of blotting. You can see the blotting device here on the Leica. It's currently in a bake out. I don't think we can run it.
It's not in the
It's not? No, we haven't started yet. Okay. But it's the same kind of setup, right? You have a chamber on the top that is humidified, and a rod that holds the, well, in this case, actually the whole chamber moves instead of the tweezers moving. But if Mahara, you want to install that.
There's a magnetic ring. I don't know if you can hear me.
There's a magnetic ring, she's saying, and the filter paper. Yeah, the magnetic ring holds the filter paper in place. You can choose to blot from the left side or the right side.
Oh, on the front side or back side.
Yeah, the front side or the back side of the grid. But you can't do both from the in the Leica.
You can see it move.
Yeah. Okay, so I'm gonna move it.
Could you get a close-up of the filter paper and see how flush it is? There was a question earlier about Leicas and filter paper. If the person is here, perhaps in chat, you can expand if you had particular questions about the Leica.
Oh, what was the question?
There's no question, but they asked last time about
Okay.
what happens when the filter paper starts to bend,
Oh,
which it does eventually.
yeah. I'm not seeing the question here, but if the filter, I don't know. I mean, if my Vitrobot filter papers are bending, depends on where they're bending. Sometimes they bend at the top, which doesn't really matter because that's not the part that touches the sample. But if they are bendy at the bottom, I might think about changing
Well,
it.
here's the opposite. It touches the top.
Okay. The filter here, it touches the top,
Yeah.
according to Mahara.
Well, it touches near the top.
So that's the Leica. Was there anything else you wanted to look at?
No, I don't see the particular question. If there's anything else you want to go over on the Leica, they're all very similar devices. The main thing is one-sided blotting versus two-sided.
Yeah, and it has the same kind of overall architecture. You have the environmental chamber. You have blotting papers. You have an arm with a tweezer here. You have your liquid nitrogen. Woo,
Sorry.
your chamber is moving. Yeah, you have an ethane cup at the bottom. Yeah, I know some people here like the Leica because you can control, or you can at least have a, there is a temperature monitor on the ethane cup. So you always know what the temperature of your ethane is, versus on the Vitrobot you have to guess. Yeah, so I think some people like that. I think it's a good idea. Yeah. Anything else?
Okay, well, if there's nothing else, we can wrap up. So we have a couple of seconds. If there are any more questions, please use the chat. Otherwise, we'll see you next time. Oh, question, finally. So the question is, when you calibrate the horizontal blot position, the paper moves as it was a real blotting, and the next position could be off due to bending of the paper due to humidity. All these devices automatically rotate to give you a new position on the filter paper. But I guess the question is, if the filter paper is not flush and you're coming into contact, well, there's a lot of force going on there. So how much would that impact? I would say normally we don't see too much bending. Eugene, would you change filter papers if you see a huge amount of bending? I guess it depends on how long your freezing session is.
Yeah. If my filter paper is really crinkly, I would change it. But I've not really experienced this problem on the VitraBot, I would say. Have you? I mean, the crinkly bits are after you blot, then it leaves behind a wet spot. And that becomes crinkly, but
I guess because
yeah.
it has the foam pads, it keeps the shape.
Yeah.
But that does not.
Yeah, I mean, yeah, Mahara was saying that it might keep the shape a bit better on the VitraBot because of the foam pads. Yeah, I would say, I mean, for me, these devices are not super consistent all the time. But if I try to do everything the same as much as I can, so if per session I make like 8 grids and then I change the filter papers every time, I think that helps to keep things a little bit more consistent. Right. Yeah, maybe if you tell yourself that you do like 4 grids and then you change the filter paper every 4 grids on the Leica, and if there is some consistency in the variation, if that makes sense, that might be characterizable for the first grid versus the 4th grid, how the ice behaves differently. But yeah, usually it's probably more variation due to other factors than this, maybe. I'm just yammering here.
There's a lot of variation in plunge freezing, and somehow it all works out in the end because we have results. So I think that is the class. So we're going to wrap up here, and we'll see everyone on Monday. We're going to be talking about a more complicated subject, and that's more on Fourier transforms and image formation. But that could also lend itself to just generally talking about what good images are and how do we limit aberrations on the microscope side to do the experiments we want to do for cryo-EM. So until then, have a good afternoon and see you next week.
Make sure you watch the videos, the Grant Jensen ones, and if you want, the lecture that I gave last year. But that lecture is basically just me taking 5 hours of Grant Jensen lecture material and condensing it into an hour and a half. It's a lot of stuff, but it is very useful to know. If you've got a background in crystallography, a lot of it's probably going to be reviewed, but good to go over.
Okay. And on that note, if you haven't let Micah know you want to be part of the journal clubs, this is the last call.
Yeah, I will be sending out assignments this week.
Okay. Have a good afternoon.